Yeah, another one.
Today, today we're going to learn about AVL trees. AVL trees are a type of self-balancing binary search tree known after its inventors, Adelson, Belsky, and Landis. This guarantees specific time complexities for our operations. Similar to red-black trees, AVL trees have a time complexity of big O of log n for search, insert, and delete. As a reminder, the definition of height is the number of nodes on the longest path from the root to a leaf node. The central property of AVL trees is that for any node, the height of its two subtrees differ by at most 1. We call this the balance factor, which is found by taking the height of the left subtree and subtracting the height of the right subtree. This means that valid values of balance factor are -1, 0, and 1. Let's take a look at an AVL tree. Note that we'll say an empty tree has a height of 0. So leaf nodes have a height of 1. I'll put the height of each node in green, and I'll put the balance factor of each node next to the height in blue. Remember that balance factor is calculated by taking the height of the left subtree minus the height of the right subtree. Let's take a look at 50. Its height is 5 because there are 5 nodes on the path from 50 to 83. To find its balance factor, we take the height of its left child minus the height of its right child. 3 minus 4 is -1. Please pause the video here if you need some time to review this. Here's an example of a tree that is not an AVL tree. As you can see, it has a node with a balance factor greater than 1. Next, let's take a look at how AVL trees compare to red-black trees. In the worst case, AVL trees and red-black trees have identical time complexities for search, insert, and delete, big O of log n. However, for amortized time complexity, red-black trees have a time complexity of big O of 1 for insert and delete. If your application is lookup intensive, AVL trees are more efficient because they are more strictly balanced. That is, the height of an AVL tree is bounded by 1.44 times log base 2 of n. Is complexity of big O of 1 for insert and delete. Time If your application is lookup intensive, AVL trees are more efficient because time more strictly balanced. That is, the height of an AVL tree is bounded by 1.44 times log base 2 of n, while red-black trees are bounded by 2 times log base 2 of n. Proving these values is outside the scope of this video, but I put links in the description if you want to know more. Also link a paper from Ben Pfaff, who used to teach at the computer science department at Stanford, where he concluded that if insertions often occur in a sorted order, AVL trees excel when later accesses tend to be random. Take a look at the paper if you're interested.
Insertion.
He compares unbalanced binary search trees, AVL trees, red-black trees, and splay trees. Let's take a look at some binary search trees, AVL trees, for our nodes, we'll hold the data in an attribute called key. We maintain pointers to the left and right child, and we also store the node's height, which is set to 1 upon creation. For the tree, we'll keep track of a pointer to the root node. The search code is straightforward and is the same for other binary search trees. I won't walk through it, so please pause the video if you'd like to review. Remember that search has a time complexity of big O of log n, as earlier we learned that the height is bounded by 1.44 times log base 2 of n. That's it for this video. In the next one, I'll cover insertions. Thank you for watching. I hope this video... Today, we'll continue the series on AVL trees and talk about insertions. Today, we're going to learn about AVL trees. Today, we'll continue the series on AVL trees and talk about insertions. If you haven't seen the intro and search video, please watch that first. Remember that when inserting and deleting nodes from an AVL tree, we may need to perform fixes in order to preserve the main property of AVL trees. That is, for any node, the height of its 2 subtrees differs by at most 1. This is called the balance factor and has valid values of -1, 0, and 1. Let's talk first about the types of fixes we'll do, and then I'll show you how to use them. First, there is left rotate. In this situation, we rotate A down and it becomes the left child of B. Here is the result of a left rotation. This is permissible because we know that the nodes in subtree Y are greater than A, but less than B. Right rotation is the same concept, but just the inverse. Let's revisit left rotate, this time with the code. Note that I've named the variables in the same way they're depicted in the diagram. The node parameter in our case is A. On these 4 lines, we rearrange pointers and set B dot left to A and set subtree Y as A's right child. We then update the height of A and B after rotation. The height becomes 1 more than the max of the left and right subtrees. Please pause the video if you need a minute to review the code. On these 4 lines, we rearrange pointers and set B dot left to A and set subtree Y as A's right child. We then update the height of A and B after rotation. The height becomes 1 more than the max of the left and right subtrees. Please pause the video if you need a minute to review the code. The code for right rotate, of course, is symmetrical. Note that these are all constant time operations. So the runtime for left and right rotate is big O of 1. I'll show you the logic for when you need to perform rotations, and then we'll take a look at some examples. Here's the insert code that encompasses rebalancing. There are two groups, single rotations and double rotations. To determine which, we look at the balance factor of the unbalanced node.
Look at the balance factor.
And how the key we added compares to the node's left or right child.
Man, this guy is good.
With this information, and double rotations. To determine which, we look at the balance factor of the unbalanced node and how the key we added.
What is BF? Balance factor. Oh.
Compares to the node's left or right child. With this information, we can determine if the tree is left or right heavy. Let's take a look at rotations in action, starting with this valid AVL tree. We know it's a valid AVL tree because the heights of A's left and right children differ by 1. Likewise for the children of B. Let's say we want to insert a new node, and based on its key, it belongs in subtree X. We add the node to X, and its height increases by 1. We got lucky because this is still a valid AVL tree.
Yeah.
However, what happens if we need to add another node into X? This increases the height of X by 1, and in turn the height of A and B by 1. We now have a violation because A and Z have a height difference of 2. This fits the following if condition. The balance
factors. Key. 100 left key.
factor is 2. The node we added is in X.
What? This is so well made. I mean, it's so easy to understand. Key was added is X.
Which is less than A, B's left child. The tree is left heavy, so we perform a right rotation. I'll move the tree over to the left and demonstrate this. Let's first move B, and Y become this new left child. We move A and make it B's parent. We'll fill in our height values, starting from the bottom and working our way up. Note that we already added 1 to the height of X after adding the new node. We calculate B's height, and since Y and Z are both H, B is H plus 1. First move B less than A. B's left child. Values. B is H plus 1. Rotation. In this case, a right rotation. Let's take a look at another example using this tree. Note that it's a valid AVL tree as all balance factors are in the allowed range of -1, 0, and 1. Let's insert a new node, and based on its key, it belongs in X. This increases the height of X by 1, as well as the nodes above X. We see that we have a violation with C's children, as the difference in height between A and Z is 2. This satisfies this if condition. Our balance factor is 2. We added the node in X, which is greater than A, C's left child. We'll fix this by a left rotation followed by a right rotation. We start with the left rotation on A. We make A the left child of B. Our balance factor.
Oh, does that mean the tree this is balancing factor larger than 1 means it's more lean to the left, but the left tree is more lean to the right. I get it. The key is larger than root left key, so I just need to. So
to
do a left rotation and then do a right rotation.
We added the node in X, which is greater than A, C's left child. We'll fix
we left rotate the left and then right rotate the root.
this by a left rotation.
So in the final case, the load factor, it's a balance factor is smaller than 1, which means the root is more heavy to the right, but the right is more heavy to the left. So this key smaller than root right key, right itself gonna be smaller to the left. I'm gonna right rotate it, right rotate root right, and then because it is more heavy to the right, we left rotate it, and then we left rotate the root.
Followed by a right rotation. We start with the left rotation on A. We make A the left child of B and X the right child of A. We fill in C and Z. We then fill in our height values, again starting from the bottom. And then we calculate the heights of the remaining nodes, adding 1 to the greater of the two heights between the children. A becomes H plus 1, B becomes H plus 2, and C H plus 3. However, we're left with more violations. Let's fix them. We perform a right rotation on node C, resulting in this tree. Again, filling in the heights, start with C. We start with the, in this case, a right rotation. 1 to the left child to the left and demonstrate this. So we perform a right rotation. I'll move the tree over to the left and demonstrate this. B is H. On our height values, again start greater of the two heights, H plus 3. However, we're left with more violations. Let's fix them. We perform a right rotation on node C, resulting in this tree. Again, filling in the heights, starting with the subtrees. A and C now both have a height of H plus 1, and B has a height of H plus 2. As you can guess, the other two are symmetrical to these. Let's take a look at the code. We start at the top of the tree at the root.
So we find first, and then we
always add a node as a leaf. So we check if we reached a nil node. If so, we return a new node with the specified key. If we haven't reached a nil node, we need to find the correct place in the tree by comparing the specified key with the key of the node we're currently visiting. If the key is less than the node's key, we make a recursive call to insert, passing in the node's left child. Otherwise, we make the same call with the node's right child. When we've reached this line, we've added the new node and go back up our recursion stack. We set the height of each node 1 greater than the max of its left and right children. We update the balance factor, taking the height of its left child and subtracting the height of its right child. Finally, we check for our 4 fixes we discussed in this video. I hope you're still with me. I know it's a little confusing because it's recursive. If you're struggling, I recommend taking the code in my GitHub and adding print statements so you can see it in action. Because we may potentially traverse all the way down the height of the tree, and we know that left and right rotate are constant time methods, we can see that the runtime of insert is big O of log n, since the height of the tree is bounded by 1.44 times log base 2 of n, as we learned in the first video. That's it for this video. In the next one, I'll cover Today, we'll continue the series on AVL trees and talk about deletions. As a quick reminder, we may need to perform fixes when inserting and deleting nodes from AVL trees. This is because for any node, the height of its two subtrees differs by at most 1. This value is called the balance factor and is found by taking the height of the left subtree and subtracting the height of the right subtree. I'll use this tree to show examples of deletion. For now, I'm going to completely ignore height and balance factor and only show the different scenarios for deleting nodes. Let's say we want to delete 60. 60 does not have a left child, so we move its right child into its place. Again, this may or may not be balanced, but for now we don't care. Let's do 15 now. In this scenario, the node has no right child, so we move the left child into its place. Lastly, let's delete node 120. This node has both a left and a right child, so we need to
remove this.
find its in-order successor. That is, the node in the tree with the smallest value that is greater than 120. You can see that this is 125. So we move 125 in the place of 120. Now let's go back to our original tree, this time filling in height and balance factor. And I'll show you a few examples of rebalancing after removing nodes. Let's delete 120 again. We move 125 in its place. It now has a height of 3 and a balance factor of 2, which we know breaks our AVL tree property. So we need to perform a fix.
What just happened? What the hell?
Here are the 4 types of fixes, which are very similar to insertion. You see that we can perform single or double rotations.
So this also left.
We analyze the balance factor of the node and the balance factor of its left or right child to determine if the tree is left or right heavy.
No, the BF alone. BF alone let us know if the tree is left or right heavy. This is checking if the left is left or right heavy, and this is checking if the right is left or right heavy.
A balance factor is 2, so this first condition is met. The balance factor of its left child is 0, so both conditions in the first if block are true. We need to perform a right rotation. Back to the full tree, I'll demonstrate the right rotation on node 125.
Yes.
We're back to the balanced AVL tree. Let's do one more example, this time deleting 10. It's a leaf, so we don't need to replace any nodes. Just remove node 10. The height of 15 updates to 1, and the height of 25 updates to 2. Traversing back up the tree, we see we have a violation at node 50, as this balance factor is negative 2. This violation satisfies this if condition. So we perform a left rotation.
So this is her to the right, her to the right, and the right is also her to the right.
The result of this rotation is the following tree, a valid AVL tree. The code for delete rotation is the following tree. A valid AVL tree. The code for delete is similar to insert. We start at the root of the tree and traverse down, looking for the specified key to delete. Once we find it, we perform our 3 checks. If the node doesn't have a left child, doesn't have a right child, or has 2 children, in which case we need to find the in-order successor. Continuing on, we update the case we need to find the in-order successor. Continuing on, We update the height of the node, as well as its balance factor. We then look for the 4 fixes we may need to perform. Finally, the runtime of delete is big O of n, as we may need to traverse down the entire tree, which, as we discussed in the intro video, is bounded on height by 1.44 times log base 2 of n. That's it for AVL trees. Thank you for watching. I hope this video helps you on your computer science journey. Today, we're going to introduce red-black trees. But first, let's review binary search trees. Binary search trees are simply ordered or sorted binary trees. These binary trees have a guaranteed height of big O of log n for n items. A red-black tree is a specific type of balanced search tree. Let's go through the criteria for red-black trees. First, nodes are either red or black. The root and leaves are always black. The leaves are simply the leaves. If a node is red, then its children are black. And finally, all paths from a node to its nil descendants contain the same number of black nodes. Let's look at an example.
All paths from a node.
Go through our criteria. Here's a root.
Ah, shit.
As you can see, all nodes are red or black. The root node, A, and all mid nodes are black. All red nodes have black children. Lastly, all paths from a given node to its nil descendants contain the same number of black nodes.
Wait, I thought leaves are black.
The root node,
A
A,
root.
and all mid nodes are black. Let's look at an example and go through our criteria. Here's a red-black tree. As you can see, let's use the root as our given node. We see that all single paths from nil nodes contain 2 black nodes. One note here. When counting the black notes in our pattern,
10 the same number.
we don't count the starting node. We call this number 2 the black height of the red black tree. That is, the number of black nodes from the root to the nil node, not counting the red cells. In fact, each node has its own black height.
Black height.
A few notes before we finish. Nodes require one storage bit to keep track of height. Second, the longest path, that is, the path from the root to the farthest nil, is no more than twice as long as the shortest path, which is the path from the root to the nearest nil. In other words, the shortest path has all black nodes, and the longest path alternates between red and black. This is because of the constraints we defined earlier. Take a look back at our example and you'll see. So how do we use red black trees? Just like any other binary search tree, there are three main operations: search, insert, and remove. Searching is no different, but inserting and removing nodes require rotation because we must maintain the properties of red black trees. We'll cover these two operations, as well as rotations, in future videos. These operations have a time complexity of big O of log n. As we said, the maximum height of the tree is on the order of log n. Finally, because we only require one extra storage bit, red black trees are a complicated topic, so I'll use several videos. To cover them. In this video, we'll learn about rotations, an important operation in inserting and deleting items from the red black tree. In case you missed my first video, here is a review of rotations alter the structure of a tree by rearranging subtrees, with the intent of decreasing the height of the tree. Remember that we said red black trees have a maximum height on the order of log n. We can decrease the height by moving larger subtrees, smaller subtrees. We won't color the nodes red or black. Instead, we'll color them so it makes the rotation easier to see. We're going to let rotate on node 5, the blue node.
Oh, it's the same.
5's right child, 10, the yellow node, becomes its parent. 10's left child, 8, the red node, becomes 5's new right child.
Wait, what?
Here's the tree after the rotation is complete.
What the fuck? What the? Oh yeah, it's the same.
Now let's walk through a right rotation.
It's the same.
Search tree are still preserved. That is, smaller nodes are to the left and larger nodes to the right.
Yeah.
Here's some pseudocode for a left rotation. Finally, rotations have a time complexity of big O of long. If you think about it, we're simply changing a few pointers in our tree. And that's it for this video. Rotations are pretty straightforward, but I think it's important to understand how they work before we dive into
Today we're
going to learn about red-black tree insertions. In this video, we'll focus on strategy. And we must ensure the tree gets rebalanced in a binary tree. A is Z's parent.
What the hell is that?
We've covered them previously, so I'll let you review them yourself.
No, it's red, black. The leaves nil are black. Red node is red. It's children are black. Damn. All paths from a node to its nil descendants contain the same number of black nodes.
Let's also do a quick refresher on relationships in a binary tree. A is Z's parent, B is Z's grandparent, and D is Z's uncle.
What the fuck?
Let's begin and discuss the high-level strategy we'll use for inserting nodes into a red-black tree. There are two main steps. First, we insert the node and color it red. Second, we recolor and rotate nodes to fix the violation. You may wonder, why do we color the node red? We know eventually we have to get back to these properties. By coloring the node red, we may break property 2 or 3, but it turns out these violations are fairly easy to fix, and you'll see how.
What the hell?
Let's break down step 2 in our strategy. After we insert the node and color it red, there will be 4 main scenarios we can encounter that will need further attention. Z could be the root, but it turns out these violations are fairly easy to fix, and you'll see how. Let's break down step 2 in our strategy. After we insert the node and color it red, there will be 4 main scenarios we can encounter that will need further attention. Z could be the root, Z's uncle might be red, and Z's uncle might be black. There are 2 different cases when Z is a black uncle. For now, ignore the triangle and line bar in parentheses. We'll cover those later. Let's discuss case 0, when Z is the root. This one is pretty simple. All we need to do is color Z black.
Damn.
Moving on to case 1, when Z has a red uncle. For this situation, we recolor Z's parent, grandparent, and uncle. You might be wondering why B is red, the root of the tree. Just note that this is a subtree. You'll see case 1 as part of a larger tree in the example video. Case 2 is when Z's uncle is black, with triangle as the identifier. Let's say this is our graph. C is black and is Z's uncle. This is what I mean by triangle. Z's parent and Z's grandparent form a triangle. This is because Z is a left child and his parent A is a right child. Couple with triangle of a larger tree. This is what I mean by triangle. Z's parent A is a right child. You might also see the triangle case like this, where Z is a right child and his parent is a left child. Same thing, just symmetrical. When we encounter this case, we rotate Z's parent, doing so in the opposite direction of Z, so Z takes the place of A. Nothing too tricky. Finally, case 3 is when Z's uncle is black, with line as the identifier. Again, C is Z's uncle, but as you can see, Z's parent and Z's grandparent form a line. That's because Z is a right child, and so is his parent A. The symmetrical situation is when they are both left children. For case 3, we rotate Z's grandparent, again in the opposite direction of Z, so that A takes the place of B. For case 3, you will need to recolor the original parent and grandparent after the rotation. That's it. Let's review quickly. To start, we insert the node and color it red. Red-black trees have certain standards, so we must recolor and rotate nodes to fix violations. There are 4 possible fixes we'll encounter. First, when Z is the root, we color it black. Second, when Z's uncle is red, we recolor Z's parent, grandparent, and uncle. When Z's uncle is black and a triangle is formed, we rotate Z's parent. And when Z's uncle is black and a line is formed, we rotate Z's grandparent and do some recoloring. Here's the pseudocode for your reference. RB insert is simply inserting the node. RB insert fix up covers our 4 scenarios. Stay tuned for next time. You'll see our strategy in action as we walk through some examples. Thank you for watching. Please subscribe if you learned something.
High bands binary search tree. Ascending order? Damn. So, does it matter? So we need to just insert, insert. It will be severely, it will be left. It will be severely left heavy.
Today, we'll continue this balance node and how
Right heavy. Right heavy. Yeah. So rotate root.
Today, we're going to learn about AVL trees. AVL trees are a type of self or nodes will hold the date 1 upon creation. The same for other binary search trees. Today we'll continue.
linear root. How are we gonna do it? I don't know. Max size none. Insert self root key.
Today we're going to learn about AVL trees. AVL trees are a type of self Today, we'll continue the series on to determine.
Node key. Wait, registering is in the root. Oh, I see. Oh yeah. It is of course gonna be one here. Um, wait, that's not right. Get left rotor, do a left rotate, right? Left rotate, something like A, B, X, Y, Z, is gonna be note note right is gonna be left. So gonna make some B A X Y Z. Some change. Wait, we're gonna yeah. Oh shit. Update that shit too. Do we have to do that? Wait. Do I need this? This is not right. Oh shit, this is not good. What the hell? Jesus Christ. Oh my goodness. Oh shit. What the fuck? What the hell?
Adding 1.
Is larger. Do I just do this? Or something? Collect rotate, yes. Return. What the hell? Oh my goodness. Let me see on the B note right. Y be left. B left node. Note right Y. Yes, I'm right. The return B. Oh, still not right. What the fuck? What is going on? What?
However,
Oh, we have to update this route. All right. What the fuck? What the hell? Is it a joke? What is going on? Please. Okay, I think it's gonna be time limited or memory. Okay, I give up. Fuck this shit. I'm out. Oh my fucking god. Just waste so many time. Oh Jesus Christ. Jeez. I gotta go eat. Guys, Jesus Christ.